Carbon, and this is my Physics 2211 Lab 1 constant velocity. Content covered would first is purpose, procedures, then physics involved in the lab, then code for a computational model, then error, and then any questions that may arise. For our purpose, we're trying to observe the motion of some object that is moving at the same speed without changing direction, and to see how in real world interactions differ from theoretical slash computational interactions. Also, to see if and check if Newton's second law remains true. The physics involved, Newton's second law of motion state is summarized with this equation: F net equals change in momentum over change in time. Eventually, you can rewrite this in as F net times change in time over mass plus v initial equals velocity final. So basically, if there's no force being applied, then v initial equals v final, so velocity stays constant. Things you may need are an object, preferably a ball or a cart, a phone to record, something to measure like a meter stick, an app. We use tracker that can track the video, the object's movement through a video. Laptop and glow script to write your code. Record a video and where you can publish, and where you could push the object and let it move in one direction. Then analyze the video with the tracker app. Second, use the laptop and go to glow script to create the code that would demonstrate the object's movement in an optimal environment, like without friction. The starter code we were given, which is right there. Third, grab all the data points and put them on some sort of graph, and then compare the findings between the experimental and the theoretical. This is my experimental. We know that velocity is equal to dx dt, so the derivative of position, so basically the slope. So we see that velocity is constant at the beginning, even like 3/4 maybe, but then towards the end it approaches 0, so decreases. Which means that there's like something slowing it down, some force. So for computational code, we were given the starter code. However, you have to make some slight adjustments. The velocity of the ball vector, I found it by using v average equals change in r over change in t. Plugged in my values and got around 0.660, and then I plugged it over here. I found delta t by dividing the total time, 1.16, by the number of intervals in my experimental, because I wanted to have the same number of intervals in both experimental and theoretical, which is right here, 0.03625. Computational continued. It had to be less than 1.16 because that was the length of the video. And to find the change in position between each change in time, I just used the formula v average equals change in r over change in time. And then I basically rewrote this in code terms over here as ball dot position equals ball dot position plus ball dot velocity times delta t. My code is right here if anyone needs it. This is how the code runs. As you can see, velocity stays constant. That's pretty much it. Results in a theoretical, velocity stays constant. Like I said, slope is constant. However, in experimental, it slows down and gets closer to 0, which could be probably on friction and air resistance. Now we got to talk about error. So basically, the system first is the ball itself, and then the surroundings are like the table and me as the lab conductor. Some error that may arise is friction and air resistance, which act against the real-world object. The tracker app is also not perfect, so it could have some mishaps, especially since it doesn't perfectly track the center of mass of the object. Also, the measuring tape was slightly bent, so the actual distance covered may not be accurate. Questions: what if we change the x and then to negative x? So we know that velocity equals dx dt. However, if we had a negative x time, the derivative of that would also be negative, making the velocity negative. So it could be represented by this graph right here. What does it mean? In terms of net force, it means that the normal force goes up, force of gravity goes down. These basically cancel out. If one or the other didn't exist, either it would shoot all the way up or go to the Earth's core. However, these are the only two forces in the computational, but in the experimental, we have force of air resistance and force of friction as well. Thanks for watching.